In the last section of this chapter, 6.8, we talk about the standard enthalpies of formation. Basically, it's the energy or the heat required to form a compound. So the standard enthalpies of formation. Guys, this is what we've been looking up in Appendix C, delta H. These are for the standard states of the elements or the compounds. So the term standard state refers to the standard thermodynamic conditions chosen for substances when listing or comparing thermodynamic data. So it's usually atmospheric pressure, 1 atm, and a specified temperature, usually around 25 degrees C. So the enthalpy change for a reaction in which reactants are in their standard states is delta H sub 0. Sometimes it can be read delta H naught. So the delta HF stands for the standard enthalpies of formation, denoted delta HF, and that little degree sign should be up above. All right, that's the standard change for the formation of 1 mole of a substance in its standard state from its component elements in their standard state. So when we're talking about a pure element and standard state, also the diatomics like H2, O2 in their standard states, which for most of them that's gases. Except for bromine, it would be a liquid, and for iodine, the standard state of I2 is a solid. So the delta H's for a pure element or a diatomic in their standard states are 0. So when we're looking up these delta HFs, these formation reactions are written with the reactants as elements in standard states with 1 mole of the product formed. So for example, for methanol, the formation of methanol, it's C, graphite, plus 2H2 gas plus 1/2 oxygen gives us CH3OH. So again, you note here that we have 1/2 a mole of something. As I stated before, when we're balancing equations, regular equations, we don't use fractions. But when we're balancing thermochemical equations, being that we want to show 1 mole of the product that's being formed, it's okay to use fractions for the reactants. And in this case, our delta HF would be equal to negative 238.6 kilojoules per mole. Again, guys, as I was saying, when we've been using Appendix C in our textbook, we are using the delta HFs, or the standard heats of formation, for these substances. If we're trying to calculate the delta H for the reaction, we have to take, and there's a lot of different symbols that are missing here. So we have to take the summation of the number of moles of delta HF of the products minus the summation of the number of moles of delta HF of the reactants. So our delta H can be calculated using the values from the back of the book. We take the sum of the products minus the sum of the reactants. Also, keep in mind that if there is a stoichiometric number of moles in front of the number, then you have to multiply your delta H by that number. For example, 2 H2Os, I would take the delta H value for H2O and multiply it by 2, and then plug it into this equation. So these formulae above, it's going to lead us into Hess's law. If you remember the lab that we were doing, and actually the lab we're going to do tomorrow, we were looking at figuring out the delta H using the Appendix C. We're also figuring out the delta H by using Hess's law, and they do support one another. So this is just a quick example problem of having to find the heat of reaction. So if you receive this kind of problem, you would either receive an appendix insert, or you would receive the information that you need for the delta H's for each of the reactants and products. Take a look at the next page to see how this is completed. So if you take a look at this equation, I need to take the delta H of the products minus the delta H of the reactants. So I put in 2 times 0, because Fe has a standard formation of 0 because it is a pure element. When I look up CO2 in the back of the book, I get negative 393.5, and I have to multiply that by 3. From that, I'm going to subtract. I'm going to put my brackets around the reactants. I would subtract the negative 825.5 for the Fe2O3 and 3 times negative 110.5 for CO. When I do the math, I get negative 23.5 kilojoules. So we've been talking about the delta HF, which is the heat of formation. It's the energy absorbed or liberated when 1 mole of a substance is formed from its elements at standard state. But there are other forms of delta H we can talk about. Delta H RXN, it's the energy absorbed or liberated when molar amounts of reactants react. Heat of combustion is delta HCOMB, or sometimes you can just see it delta HC. It's the energy liberated when 1 mole of a substance is oxidized completely. And the last one, heat of solution, delta HSOLN. It's the energy liberated or absorbed in 1 mole of a substance dissolved completely in a solute. Okay guys, and that ends it for this chapter. So make sure you do your AP practice problems in preparation for our test. Remember that we're going to break our test up into 2 sections, the multiple choice section and the FRQs. If you did the AP practice and you kept up with the problems in the book, you should be well prepared for both of these.